And as we float our way through arc functions in the trigonometric realm, I guess we're going to have to look at arcsecant. And arcsecant's a little bit harder, I guess, to imagine, or at least for me. When I think of the secant function, I have to think of the sine cosine function. So I'll start with the cosine function doing its thing. And we realize that secant is 1 over cosine, so it's going to develop asymptotes here, here, and here. And we need one place where it does not repeat. And so what we're going to pick where it doesn't repeat, well, let's just draw the function itself, I guess. Let's get the 1 over part going. Shoots off to positive infinity here, shoots off to positive infinity here, shoots off to negative infinity here, and shoots off to negative infinity here. So if I cap it here and here, if I go from 0 to pi, I get a complete set of the secant function. And what it's doing is it's going from 1 to negative infinity between 0 and pi over 2. And then from pi over 2 to pi, it's going from negative infinity to 1. So if we try to graph the arcsecant function itself, like I said, this is a harder one for me to visualize. First off, the domain for the secant function, one period is going to be between one period without repeats is going to be between 0 and pi. But we have to realize this domain is broken by pi over 2. So there's what the domain looks like with the asymptotic jump in the middle. And then the range it spits out, well, it goes from negative infinity to negative 1, and then it reemerges at 1 and goes off towards positive infinity. So I need to go from negative infinity to 1 in my arcsecant function. So the arcsecant of x here. And so it's going from negative infinity to 1. And at negative 1, right, notice here, at negative 1, it comes down towards negative infinity. Well, it's emerging from pi over 2. So if I make this pi over 2, and it's working its way towards 1, and at its biggest value it ends at pi. So we'll put pi here. Then this function's going to come up asymptotically from infinity and at negative 1 reach pi. And then it's going to have a similar thing on the other side of pi over 2. It's going to come up from 1 and go off towards positive infinity. So you have this thing that doesn't really exist between negative 1 and 1, but comes in from negative infinity and pops up at pi, and then comes in from 0 and approaches that pi over 2. And pi over 2 is the thing that it's asymptotic towards. All right, let's look at its derivative. So we're going to say that we're going to make this our arc function, which means the function that it came from will be secant x. We'll look at the derivative of secant x. Which is secant x tangent x. So these are the things we need to know going into this. Let's take a couple of ways to look at it. I like your book. Your book decides to take this definition here and reverse it. It's going to say that the secant of y is equal to x. That's the reverse definition of this. All right, if I apply the secant of y to both sides, the inverse functions cancel each other out, and we get this. Then we'll take the derivative in terms of x on both sides. And so we get the derivative secant y tangent y dy dx, taking it explicitly, and we get 1 on the other side. That means our derivative dy dx is 1 over secant y tangent y. And now we want to replace this in terms of x. So what we have to look at here is, right, we're in terms of y, but we want this in terms of x. Well, the first substitution we can do is this is 1 over x. And the other thing is, well, we go back to our Pythagorean identities, and we know that tangent squared x, 1 plus tangent squared x equals secant squared x. Solving for tangent, tangent squared x equals secant squared x minus 1. So tangent squared, or I'm sorry, square root of tangent squared of x is the square root of secant squared of x minus 1. So tangent x equals secant squared x minus 1. Right, and because what has been our job is been trying to get this in terms of secants, because we know what secant is, because we know secant is x. And so this is x squared minus 1. And we have the ability now to get an answer out of this. Now, what's going to happen here, though, is something unique is going to happen. If we look at how this function is working, this has two different things happening because of how big x might get here. And what happens with negative x's and positive x's. So this actual answer, because all of these are positive, looks like a composite function where you get the positive answers from the square root. You get a plus or minus. Whenever you take a square root, you get a plus or minus. So we talk about the positive answers come whenever x is greater than 1. And the negative answers is when x is less than negative 1. But this here could really be changed if we change the sign out front, because that's the only thing interacting with these signs. And so we say the derivative of the arcsecant is 1 over the square root of x, the absolute value of x times the square root of x squared minus 1 for the absolute values of x, with x being greater than 1. The absolute value of x being greater than 1, which is what we got for the graphs. The chain rule does apply to this, and so that means that secant of u is equal to 1 over the absolute value of u, which will be a whole function, times u squared minus 1 du dx. And so there's our arcsecant. All right, I'm going to stop this video. We'll put arcsecant up, and what I'm going to do is a quick look at arc cosine, arc cotangent, and arc cosecant together, and then we will add our arc functions to our list of things to do, and then we'll play with them.